Welcome to another lecture on molecules in motion. What I would like to inform you that whatever lecture class was there on 30th, we did not take up the effects of the Debye-Falkenhagen theory. What effects are going to be there if we have the Debye-Falkenhagen expression. We had skipped this in the 30th lecture. It would have been better if we had taken up this earlier, because we wanted to continue with the Debye-Falkenhagen theory and then go over to applying the molecules to uncharged or charged molecules to non application of electric field. So, before you can take this lecture to be supposed to be a little earlier than the 30th lecture. Anyway, what we are going to be discussing here today is this is the expression which we had derived from the Onsager theory, that is Debye-Falkenhagen theory. Debye-Falkenhagen theory was modified and we got the Onsager theory, which from which we got the expression of molar conductivity. We have seen how for various 1,1 electrolyte this equation can be taken up and to a great extent can be satisfied with whatever we see in the observation through experiments. So, these two parameters which we have in the Debye-Falkenhagen theory was parameter A and parameter B, and parameter A and B were actually contributions from the asymmetric effect and the electrophoretic effect, which we associated when a system of ionic charges are there in a solution. So, I will not go into the detailed discussion because we have already taken it up in 29th lecture. So, we have this equation, and now based on this equation we will see what are the parameters in under which the electrophoretic effect or the asymmetry effects are going to be exaggerated or it will be diminished under the various conditions. I think these conditions need to be understood before we take up a system where we are not dealing with any electric field associated. If we do not have any electric field associated, then obviously we are not talking about the asymmetry effect or electrophoretic effect in the solution. So, we will take up whatever we continued in the 31st lecture in the next lecture, but today we are going to be discussing on the parameters which are going to affect the molar conductivity given by the Debye-Falkenhagen theory. So, this is the equation which we are going to see, and we are not going to come back and discuss about what A and B stands for. Obviously, A and B are given to you. This is the in which you have the viscosity coefficient along with the dielectric constant of the medium, and T is the temperature. So, this was the expression which we had talked about was coming from the asymmetric effect, and this was the effect which we are associating with the electrophoretic effect. So, what happens when you have a highly concentrated solution of electrolyte? If the solution is not this equation which we had seen for the Onsager theory was, we had seen how it was verified or validated when the solution was very dilute. What happens under the condition when the concentration is very high? If the solution concentration is not dilute, then the motions of the ions are retarded. The electrical attraction between the opposite signs, the relaxation effect, the symmetry effect, and also because of the positive charge and negative charge associated in the opposite direction can carry some solvent, that is the electrophoretic effect. So, because of these two effects, what happens? In the solution you have a large number of ions in which are in motion, and because of the asymmetry effect, because it is a charged ion, they are moving under an electric field. Because of the charged ion moving under the electric field, if you have a numerous number of ions instead of being a very dilute solution where you have ions fairly distant apart, when you have the concentration high, the ions are much closer. So what happens? The electrical attraction between the opposite ions are there. Ion is associated with the ionic atmosphere, and the positive and negative ions also, not only the ionic atmosphere, but the charges themselves will have the solvent molecules tagged along with them. So both these effects will be intensified as the concentration of the solution is increased, because all these retarding forces, as you remember, relaxation forces and relaxation effect and electrophoretic effect are actually going to be opposite to the movement of the charged ion and the electric field. So they always will tend to retard the motion of the ions under electric field. So these retarding forces are going to be increased when you have an increased concentration, and if you have something which is going to pull you back, these forces are much more, then what happens? The mobility of the ions is obviously going to be affected, they are going to decrease, and if the mobilities of the ions are affected, mobility is directly related to the conductivity, so the molar conductivity will decrease. Okay. So the increased concentration of the electrolyte will have an impact of reduced conductivity, as you have already seen when we had graphs for molar conductivity versus concentration. At much higher concentration, you had the values of molar conductivity much lower than at lower concentrations. This is one effect. What happens with the temperature? So if you have the molar conductivities, the molar conductivities increase markedly when you increase the temperature. Why does it so happen when you are talking about, say, ions other than, say, positive H plus and OH minus, which is in the solvent, which are different, they propagate through the solution, move through the solution in a different manner, which we have discussed. It is the Groth's mechanism through which they move. So it is by transfer of charge or hopping of charge that they conduct. So if we are talking about ions other than the H plus and OH minus ion, what is happening? Why do the molar conductivities show a marked increase when increase the temperature of the solution? The increase is principally the consequence of decrease in viscosity of the medium. So whenever we have a medium, when the medium is supposed to be having some viscosity, so when we increase the temperature, what happens? The system or medium has a lower viscosity, they become thinner. So if they are becoming thinner, the medium, the retarding forces which they are going to be associated with the higher viscosity is going to decrease. So when we increase the temperature, the solvent medium is going to have a decrease in viscosity, and this decrease in viscosity, because both the motion of the ionic atmosphere and ions are increased, hence the molar conductivities are also going to be increased. So when you have a thinner medium, the coefficient of viscosity of the medium is lower, then the ions and the ionic atmosphere can move faster, and if they move faster, then the ionic mobilities which we are going to see is going to be increased. So when you have an increase in temperature, what we essentially are associating with is the viscosity of the medium. Whenever there is an increase in temperature, the viscosity of the medium is decreased, and if the viscosity of the medium is decreased, the motions are less restricted, and whatever effects which we are associating with the solvent, like the electrophoretic effect, will be much lower. So we have a lowering of the retarding forces, hence the conductivity, the mobility of the ions are increased, and hence the conductivity of the ions at higher temperature is increased. So the temperature effect is understood. What happens when you have a pressure associated with? We are doing all the experiments under normal atmospheric pressure. What happens when you are increasing the pressure of the system? You have an electrolyte system and you are increasing the pressure of the medium in which you are doing the measurement. So, what happens with the observed value is a decrease in the molar ionic conductivity. This also results because of the viscosity effect. When you increase for a liquid, usually when you increase the pressure, the viscosity of the system increases. So, if you are increasing the pressure, the viscosity of the medium increases, and since the viscosity of the medium increases, the forces which are going to be letting the ions propagate through the solution are going to be more effective, so they cannot move. So, when you are increasing the pressure, you have a decrease in the ionic conductivities associated. The conductivities of H plus and OH minus have larger temperature coefficients, like it is around 14 to 16% respectively, because of this difference, because of the difference in the conductive conduction mechanism. Their temperature coefficient means that for small range of temperature, how much is the increase in the molar conductivity. So, molar conductivity increase is quite large because of the higher temperature coefficient of the H plus and OH minus associated, and this is only because this is subjected to because of their mode of transfer through the medium, that is how they are conducted through the Hobsbawm mechanism. Okay. Now, there is another effect which we should be talking about, is what happens to the molar conductivities. We are talking about the molar conductivities keeping in mind whatever the expressions or the postulations were put forward by Debye-Falkenhagen theory. Debye-Falkenhagen theory, as we have seen before, is valid or validated only under very low concentration of the electrolyte, very dilute solution. So, what happens if you are having a solution and you have a increase, because we are talking about ions moving under influence of electric field. So, what happens if the electric field is increased? This effect which we see on the molar conductance or molar conductivity of electrolyte when there is an increase in electric field is known as the WIEN effect. And this WIEN effect was further extension of whatever we had seen by the Debye-Falkenhagen theory. The concept of ionic atmosphere, which was proposed by Debye-Falkenhagen theory, was further substantiated by the WIEN effect. Under very high applied field to the order of e to the order of 10 to the power 7 volts per meter, the ions move much faster. Okay. The ions will be, because it is if the potential applied is very high, what happens? The ions are going to be rushing towards the respective electrode. So, if the positive ion is supposed to be moving towards the negative electrode, it is going to be accelerating because of the high electric field applied. So, the ions move so fast that it effectively loses the ionic atmosphere which it is surrounded with. And you have to be understanding this, the ionic atmosphere which we are associating, we are not disturbing that if the electric field is not that high. They move along with the ion, and because of the asymmetric effect and the electrophoretic effect, they tend to, these two effects associated with the ionic atmosphere tend to retard their motion through the solution. Now, if we have a very high electric field, what happens? As a finite time, the relaxation time is required for it to form around the central charge. You need a definite time for it to form around the central charge. It is very small, but it does take a little amount of time for the ionic atmosphere to be formed along the central ion. That is the reason why, if you are pulling the pulling the central ion towards the electrode, then the ionic atmosphere previously has not decayed, and in the front it is not completely formed. if this is the condition, you see the decay also takes time and the formation of the ionic atmosphere also takes some time. This time is known as the relaxation time. This relaxation time is not going to be available if you are having a very high electric field associated. What happens? The ions are moving so fast that the ionic atmosphere does not get the chance to form around the central ion. So, the asymmetry effect associated with the ionic atmosphere also disappears. Hence, the solvents, the retarding forces which are supposed to be there associated with the asymmetry effect or the relaxation effect will not be visible to us. So, this effect is known as the WIEN effect. Thus, the molar conductivity of electrolyte are observed to increase when we are increasing the electric field in the orders of 10 to the power 7 volts per meter. Am I clear? So, the WIEN effect is an extension or further substantiation of the Debye-Falkenhagen theory. Here we are not talking about the electrolyte concentration as such, we are talking about the electric field associated. If the electric field applied is very high, then the ions are going to be rushing towards the respective electrode, opposite electrodes, like positive ion moving towards the negative and the negative ion moving towards the positive electrode. This will be so fast that the time required for the formation of this ionic atmosphere will not be available to the ion. And if the ionic atmosphere is not available, then these ionic atmosphere is actually what is the root cause for having the retarding force to drag the ion back when it is under influence of electric field. So, if the ionic atmosphere is not formed, then this drag forces are not available. That means the asymmetry effect which you are going to be seeing will be visible. So, if these retarding forces are not available, the molecules will or ions under the electric field will be moving much faster, will be accelerated, and if the movement of the ions is accelerated, the molar conductivities will increase. So, the WIEN effect is essentially talking about having the molar conductivity increased at high applied electric fields. Okay. Now, another effect, the Debye-Falkenhagen effect. This is also a substantiation or extension of the Debye-Falkenhagen theory. Here what we are talking about, how the molar conductivity of electrolyte is going to be affected when we have high frequency. Similarly, the molar conductivity of the electrolyte here also will increase as the frequency is increased. Okay. The Falkenhagen effect is associated when we are applying a very high frequency. It's in hertz, which is the frequency which we are talking about in terms of the electrical field. So, the frequency at which we are using alternating current. So, the frequency by which we are going from a clockwise and anti-clockwise field is going to be affected. So, what happens when you have a high frequency in the order of 10 to the power 6 hertz, that means when we are going to see the Debye-Falkenhagen effect when we have the frequency associated in the order of megahertz. So, at high frequency the ions change its direction of motion as quickly that more sluggish ionic atmosphere cannot adjust and follow the motion of the ions. The ions then move as if it had no ionic atmosphere associated, and the associated retarding force which is associated with the ionic atmosphere is not prominent, and then hence you see a molar increase in the molar conductivity. You are understanding what I am saying? When you have a frequency, suppose we are doing the experiment, obviously all the experiments are done in AC current. So, if you are having the frequency which is once it is going to be clockwise, it is going to another time it is going to be anti-clockwise. If the frequency is high, then the ions are going to be moving in one direction, and as soon as the frequency is changed to the anti-clockwise, then it moves to the other direction. But what happens if you are having a very high frequency, the change of moving from clockwise to anti-clockwise will be so fast that the ionic atmosphere which is going to be associated with the ion will not have sufficient time to adjust to the change in frequencies. And if such a effect is seen, what happens? The motion of the ionic atmosphere gets disturbed. It doesn't get a time to form when the positive charge, the clockwise frequency is applied, and when the anti-clockwise frequency is applied, then the charges are so, if the changes are so fast, then the ions cannot adjust to the changing in the frequencies of the applied field. So, what happens? The ionic atmosphere associated does not have any effect on the motion of the ions. The motion of the ions does not get retarded, and hence the mobility of the ions in the system will increase, and if the mobilities are increasing, the molar conductivity will also increase. So, at high frequencies, both the asymmetry effect and the electrophoretic effect become absent, as the ionic atmosphere associated with the ion does not get the time to be completely formed. So, under these conditions, the molar conductivity is supposed to increase, as the retarding forces associated with the ionic atmosphere do not exist to hamper their motion, and hence the molar mobility of the ions in the solution increases, and hence the molar conductivity of the ions in solution are increased. So, what we have seen? We have seen the effect of concentration, we have seen the effect of temperature, we have seen the effect of pressure, and high field and high frequency. These are going to be modifying, or whatever we see as the deviations of Debye-Falkenhagen theory, whatever we see in the experiment and what we have proposed through the proposed equation will not match if any of these parameters are going to be applicable or effective when we are doing the experiment. Okay. So, in principle, molar conductivity of electrolyte in non-aqueous solvent, if you are seeing in a non-aqueous solvent, what happens? We have so far discussed all majorly in the conductivities in the solvent, which is water. So, if what happens when we are having a aqueous solvent, the effects which can be associated with that is, one of them is the viscosity of the solvent. Similar to aqueous, molar conductivity of electrolyte in non-aqueous solvent is also expected to decrease with increase in viscosity. So, if you are having an increase in viscosity, the molar conductivity is going to decrease, as is in the case of aqueous medium. Because it is evident from this expression, molar conductivity is going to be ZUF, and ZUF can be related to, from the Stokes law, is the viscosity is always in the denominator. So, if you have an increase in viscosity, obviously the molar conductivity is going to decrease. So, what happens is, next is the dielectric constant of the solvent. If the solvent is low dielectric constant, then lessening of the degree of ionization of the electrolyte. Electrolytes are completely dissociated in water, may not be completely dissociated in solvent, it may be only partially dissociated, having low dielectric constant. So, suppose we have a solvent of low dielectric constant and compare that with water. Water has a very high dielectric constant. So, in solvents which have low dielectric constant, the degree of ionization, that means formation of ions in the solution, gets hampered. The electrolytes that are completely dissociated in water may not be completely dissociated in a solvent which is having low dielectric constant. For example, HCl is a strong acid, C 10 to the power 3 is the dissociation constant, it is completely dissociated in water. However, in ethyl alcohol what happens, because of this, this is not, does not behave like a strong acid, it is behaved like half the acid strength of what we have in aqueous medium. So, the dissociation constant is of the order of -2. So, you can understand, suppose two ions with positive and negative charges at a distance r, the medium of the dielectric constant of the solvent, the energy of interaction between the two ions. Okay. In a medium of dielectric constant, say epsilon of the solvent, then the two ions which will interact is going to be given by the interaction energy is going to be given by V equal to minus Z square E square divided by, you see the dielectric constant of the medium is in the denominator. So, what happens if you have dielectric constant which is large like water, the ions may come rather close together before the energy of interaction becomes appreciable. If we choose ethyl alcohol, for which the dielectric constant is 24, at the same distance of approach the interaction energy will be say 80 by 24, 33 times greater. So, alternately we can say the energy of interaction between becomes appreciable at a distance of 3.3 times greater than in water. So, what happens if the dielectric constant, as a result most solvents have much lower dielectric constant than water, and effects due to the ionic interaction is much larger in water. So, the ionic interactions which we are seeing, which is supposed to be much higher in when we are talking about solvent, but this interaction energy if is going to be lower if the is going to be if the dielectric constant is lower, this interaction energy is going to be higher, and if for water this is pretty high. So, the interaction energy is going to be for water this is high, this is high. So, this is the energy of interaction between the ions is going to be lowered, and what happens is the energy of interaction becomes appreciable at a distance of, for if I compare water and ethanol, it is appreciable at a distance of 3.3 times the greater that in water. So, most solvents as a result, most solvents, since most solvents have dielectric constant lower than that of water, the effects due to ionic interactions are much larger in water compared to the other solvents. So, if we see the effect of dielectric constant coming from the Debye-Falkenhagen theory, large ionic interactions will often render the Debye-Falkenhagen equation useless. It is still presumably correct for the extrapolation of to get the extrapolation value of the molar conductivity at infinite dilution. The solutions for which the Debye-Falkenhagen equation is valid are so dilute that it cannot be possible to obtain a reliable measurement of their molar conductivity. In these cases, the special methods are to be used to find out the lambda naught value. The electrolytes, if the electrolyte is weakly dissociated, the limiting value of molar conductivity can be applied found out by using the Oswald dilution law. In ions with low dielectric constant, we also have ion association is occurring. This appearance of ion pairing like A plus, B minus and triple ion of this sort of configuration may result in rapid variation of molar conductivity with concentration, because of the association which is effectively there going to be much higher when you are having a lower dielectric constant. So, the ions themselves get associated, they appear as triplets or double ions. So, if these ions are there, then the molar conductivity is not going to be having a very rapid variation with concentration. So, these are effects which are going to be associated when you have a non aqueous solvent mediums. So, large interactions are going to be there when you are having the low dielectric constant. Ionic interactions will be higher. Most of the times the Debye-Falkenhagen equation cannot be valid. We cannot find out the limiting value of molar conductivity through extrapolation. Usually if it is weakly dissociated in this medium, then we can use the Oswald dilution law, which we have used here. If we know the ionization constant, we can find out the value from the plot of 1 by lambda versus C lambda in the x axis. So, this is using the Oswald dilution law, we can find out only when the solvent medium is not aqueous. So, solvent we have you do not need to think about what it should be. Just remember, any solvent which we are talking about is going to have a dielectric constant lower than water. If the dielectric constant is lower, the ion-ion interactions are going to be much stronger. If the ion-ion interactions are going to be stronger, then the Debye-Falkenhagen equation fails. Then the substance, the salts which are supposed to be behaving like a strong electrolyte may not be completely dissociated in the non-aqueous medium. There may be formation of charge association and formation of ion pairs, ion triplets. So, these will cause to have a rapid variation in the molar conductivity as the concentration of the electrolyte is increased, because if you increase the concentration of the electrolyte, system becomes much more complex. Thank you so much.